It's my great pleasure to have Berkay Celik giving the CPSRC invited talk. So he's an assistant professor of computer science at Purdue University and co-director of the Purdue Security Laboratory, and as well as part of CERIAS, which is a very famous, I guess, an old security center, one of the oldest, I guess, probably security university centers, focused on security. So he has been doing a lot of interesting work in a lot of areas of security, but intersections of a lot of IoT, CPS security, robotic vehicles, autonomous vehicles as well. He received the NSF Career Award and the Google Aspire Research Award in 2021 and 2023. And right now, we're very happy to be collaborating with him on a small sub-award, I guess, from the Tracer Center, Department of Transportation Security Centers. So with Berkay, Daniel, and well, I forgot the other professor Purdue.
Yeah, Satish. Satish is here.
Satish, yes, thank you. So very excited to be working with you and looking forward to your insights on this problem. So yeah, without further ado, yeah, please take it away whenever you're ready.
All right, thank you. Thank you for the introduction. So hi everyone, I'm super excited talking today with you. I have never been in University of California, Santa Cruz before, and hoping that one day I will visit you in person as well. So today's talk is about compositional secure autonomy. This is a part of research doing my NSF career. It's a kind of like a long vision. But today I will introduce you like some of the work we have done in a few years. So if you look at the past decade, what we have seen is the rise of smartphones, and then these wearable devices, voice-enabled devices that everybody uses right now. But if we look at like a little bit closer, what we see is self-driving cars are on their way. We have some drone applications supported by some swarm applications as well. And also in industrial control system, everything seems to become automated. So I call these systems like autonomous systems, but basically they are particularly, I would say, a part of Internet of Things or cyber physical systems as well. So these systems are magic. So if you look at the details of these systems, I mean, they follow the paradigm of sensor computation and actuation programming model. So the sensor senses the physical environment, and then these are sent to the controller, which makes some computation, and then you actuate it. However, when we look at these systems are actually complex systems. What we see is there are multiple interacting components, and these components might be done with different vendors, might have different controllers as well. And also the number of sensors and actuators are diverse. And each component might access to a subset of sensors and actuators. So all these information are fused by the controller, and then an actuation command is sent. Even a little bit, if we look further, what we see is most of these systems try to be more interactive and collaborative as well. So one example is the V2V, right? We are talking about collaborative perception, sending information to each other to increase the safety of them as well. So another thing in composition, what we see is the components interact with each other, but also these components include some learning-enabled components as well. This makes things a little bit different than what we have seen in traditional systems. But the problem here, when we look at all these systems, the developers wants to have vulnerability analysis or security guarantees for the entire system. Unfortunately, what we have seen historically is if you make each individual component secure, this doesn't really mean that we are making the whole system secure. So this requires understanding how these individual components interact with each other, what data they send or share to each other, and then reason about the security. So this is basically system-wide security And the goal is like how we can achieve in these autonomous systems. So for this reason, in this talk, I would like to first talk about how this composition manifests itself in autonomous systems, and also how we can produce proof of correctness that ensure the composition of these individual components adhere to safety and security properties. And I will demonstrate some examples to you from some robotic vehicles and also self-driving cars. Before going into the details, in order to answer these questions, my research approach is as follows. First of all, given a system, we try to understand each component in detail, right? And then we sometimes lift through static analysis these components to a model. So this model represents the model of the individual component. Then we create a unified model. On the other hand, we also apply dynamic analysis to run these components or the system as a whole in a simulator, and then we monitor them, and we collect some trajectories out of this. Once we have these models and trajectories, then now we can leverage some methods in order to reason about the security. Of course, if you would like to use these models and trajectories, you need to kind of have some inputs, parameters, and also environmental factors as well. Apart from that, you need to define some specifications or properties. This might be some security specifications, or this might be some safety specifications as well. And these are the methods that we can apply. For instance, in order to test the fidelity of your approach or your model, you can apply some conformance testing. So there are delta epsilon closest metric. You can see whether your model really represents the real system or not, and then you can introduce some corrections. In order to check these properties on the trajectories or model, you can apply falsification or verification, depending on the complexity of the program as well. Also, you can leverage some data-driven approaches in order to introduce some detectors, or in order to reason about the intrusions or anomalies in these systems as well. So let's start with an interesting topic from robotic vehicles. So when we start this research, what we have seen is many researchers actually focus on traditional software vulnerabilities. So these are basically memory corruption vulnerabilities. But our analysis of GitHub commits reveal that in most cases, what we see is there are a lot of logic bugs. These logic bugs basically doesn't cause any crash or memory corruption, but leads to undesired physical behavior. Okay. So here you see an example of a specification which is actually violated in the drone control software, which we represent as a metric temporal logic. A vehicle must not deploy a parachute when the vehicle is in flip or acro flight modes or climbing. So if you do that, this will cause some issues. Probably the drone will crash. So the goal is this: how we can identify such property violations given a drone control software. Here you can try to leverage a model, and then you can use some existing techniques in order to check the properties. But the problem is that the robotic vehicle software is too complex. And if you really want to have a system level, which means that all these interacting components will be considered for property violation, unfortunately, the model-based approach might not be practical. So what we thought is we can fuzz, right? This is a software testing methodology. You generate some inputs and you have a bug oracle, and then you get a feedback, and then you mutate your inputs, and then with the goal of trying to find some bugs. But historically, all fuzzing approaches are for traditional vulnerabilities, software vulnerabilities. But our goal here is property violations, right? So what we have seen is we said, okay, we will leverage some techniques from fuzzing and then some techniques from formal methods in order to create a framework which will basically identify the property violations through fuzzing. So if you look at the figure below here, as you see, a drone accepts 3 types of inputs: user comments, environmental factors, and also configuration parameters. And then these inputs propagates to the control algorithm, and then the control program basically issues some commands to the motors. Okay. Our goal is, because we would like to try a kind of like a holistic design, we want to consider all of these inputs so that we can identify the property violations effectively. So to achieve this goal, we created PG fuzz, which is basically policy guided fuzzing. It has 4 different components. First of all, by reading the documentations, okay, we come up with some MTL formulas. These MTL formulas defines the correct behavior of the RV. And this is all manual effort. 2 of my students worked together and then extracted like over 50 different formulas from these documentations. The second step is we will mutate the inputs, but the input space of a drone is huge. So we need to have some techniques in order to reduce the fuzzing space. And additionally, in contrast to the code coverage that is found in traditional fuzzing frameworks, we need to define an oracle as well. Thereafter, we can mutate the inputs, and then we can get feedback. And then based on that feedback, we continue mutating the inputs until a policy violation happens. So let's look at these steps together in detail. First of all, given a kind of MTL formula, we just decompose into the policy into states. For instance, the policy on the left might have some related states such as parachute, flight mode, and altitude. The second step is this. We would like to identify the states that are affected by each configuration parameter. Again, the input space is like over 1,000 inputs. So we would like to reduce in this way. Given a policy, we don't want to fuzz everything, but we would like to mutate a subset of the features. So in order to achieve this, what we have done is we applied backward taint tracking. So for instance, given a state altitude, we first of all taint all the variables found in this assignment, such as the temp. But temp is not a configuration parameter. So we go backward until if we find a configuration parameter. So it means that this configuration parameter really impacts that state. For that reason, if a policy includes altitude, we need to change this configuration parameter, but we can ignore the other ones. Here, the ground temp is a configuration parameter, and it is propagated, as you see, to the temp. Therefore, we need to change the ground temp if a policy includes altitude. The second step is this. We would like to also reduce the environmental factors or user comments that we need to mutate based on a policy. So the goal is now, okay, which environmental factors and user comments impacts the state? So unfortunately, we cannot just do code analysis and figure this out. What we do is we run the simulator, okay? And then after we run the simulator, we observe the states. And then through this method, we try to kind of understand this mapping. So given a state, we know which user comments or environmental factors are relevant to that state, so that during the policy checks, we can only mutate those inputs. So this really reduces the input space and then makes the approach very effective. And the second thing is defining an oracle. So we have a subset inputs now, we mutate, but we would like to understand how we are doing. Are we close to the policy violation? So here simply we leveraged some methods from formal verification. What we say is, if a state is achieved, basically we give a 1, and if it's not true, we give -1. Okay, this is true for binary states. And if the states are some numeric values, we leverage the property here like P3. Okay, so we call it this like propositional distance. And we kind of merge them together. We merge them together in order to define also a global distance. This global distance basically tells us if whether there is a policy violation or there is no policy violation. So our oracle is also ready. So now, having our policies, and for each policy, we know which inputs to mutate, and we have our oracle. we just need to find some robotic control software and then basically assess the effectiveness of our approach. So for this, we use 3 types of control software: ArduPilot, PX4, and Paparazzi. We defined 56 MTL policies, okay? We fast 48 hours. And then we found 14 policy violations. As you see here, like for ArduPilot, for instance, we have like over 100. And then the developers acknowledge, we reported all of them to the developers. Developers acknowledge some of them, but some of them, they find that like, this is not required, very difficult to exploit by an adversary, so we will not do that. Or if we fix this, there will be some performance issues. So they didn't want to fix them. So on the right, there is a video that I would like to play and show, you know, like one of the policy violations. Basically, what happens here is that if there is a GPS signal not lost, the drone must trigger GPS fail-safe state. So this GPS fail-safe state, you can think about a kind of recovery and response action, okay? When the GPS is lost, it switches to another EKF, maybe using the IMU sensors in order to predict its velocity or position. However, an attacker can basically change the configuration parameters to some values because the developers doesn't have any bound checks on that. And whenever the GPS is jammed, or maybe this might happen naturally as a safety problem in, you know, crowded cities where there are many big buildings, the drone deviates from its path. So this is a simulator, software in the loop simulator that we are doing. As you see, we define a route here, a circle for the drone. And now what we are doing is we are changing the parameter value, and also we are blocking the GPS. The drone first keep floating in the air. But then when the GPS signals come back, as you see, it deviates from its deviated path. So this might result in some crash in a swarm environment. If there's a building, also there might be a crash as well. Okay, so the approach that I introduced was called PGFAS. Basically, this was finding the logic bugs. We have a couple of follow-up works. We try to patch these logic bugs in an automated way, which we call PG patch. And also when we are doing these experiments, we realize this. When we patch something, we are fixing a bug. However, this patch might introduce some other bugs. Okay, sometimes this is called regression bugs. For that reason, we create a kind of framework which ensures that the patch generated doesn't cause any other issues apart from fixing the original bug. So this framework is called patch verif. So if you are interested in, you know, like this, our work of basically automated patching and validating of those patches, you can check my papers on these topics. So as I said, developers basically hesitate to fix some of the bugs or logic bugs that we have reported them. And when we look at those bugs, these bugs were most of the time includes spoofing the sensors, okay? The developers were basically saying that to our comments, how these sensor spoofing attacks will affect the control of the drone. And then they really having issues to reproduce these sensor spoofing attacks. So this observation kind of contrasts with our community, because what we see is in recent years, there are a lot of attacks for sensor spoofing. These are like acoustic noise injection attacks or unintentional electromagnetic interference attacks and so on. Even in last year, we have 2 papers about this topic. So this kind of like create a research question, you know, like why these RV developers think like that. So to better understand the end-to-end propagation of these sensor spoofing attacks, what we have done is we created a reachability analysis framework. So this reachability analysis framework doesn't work on a model, but it considers the source code of the control software and tries to understand from starting from spoofing the attack, in order to reach to the end goal, which might be crash or position deviation, these spoofed sensor values visits which of the components and how those components are impacted by these spoofed values. So this is the goal. So we leverage a lot of ideas from the reachability analysis, but our job is easier because we don't have a model, but we are using the actual control software in this case. So if you look at the robotic vehicles, you will see a lot of different sensors: gyroscope, accelerometer, magnetometer. And even like very small drones leverage multiple of them. Okay, so this is number one. Number two, these sensors are used to obtain different state values. Okay, so you can use gyroscope, for instance, in order to obtain the angular velocity or the position, which is latitude and longitude. So each of them fused together, and then you obtain a state. So these state values are basically used in order to give some commands to the drone. Okay, so let's look at a little bit in detail. So as you see on the left, we have some sensors such as accelerometer and gyroscope. And if you look at the gyroscope in detail, every gyroscope is implemented in different way. So there are some hardware differences. Some of them has like some filters, the other doesn't have some filters. Also, depending on the drone, these sensor values are basically transferred to the operating system using different paths, such as SPI or I2C. Okay, so the operating system also gets these sensor values from the sensor in different ways. For instance, a sensor might buffer, and then operating system might pull them, or operating system can also buffer and then send to the control software. So there are lots of different implementations. As you see, on the control software side, there are also a bunch of filters, and there are a bunch of different EQF implementations as well. So whenever you are spoofing, you need to be sure that all of these components need to be bypassed in order to have the final goal. And the reachability analysis basically outputs the reachable states, which component this sensor spoof go as an input, and then how it is outputted. So our framework basically can give you such detailed descriptions and the states. So what we have seen is this. While sensor spoofing attacks, because you are manipulating something, right? You would like to observe something on the end states. Actually, it's not that easy, because this depends on multiple factors. RV type, sensor type, as I explained to you, each sensor uses different filters, right? Like the operating system that the drone is using, which is R2S. And then also the control software can implement different type of filters in order to remove the uncertainty or the noise on these sensors as well, such as low pass filters, or they take sometimes average of these sensors. And these filters even can be combined together, okay? So these are the 7 things to make the attack successful. Of course, depending on how you're gonna manipulate the sensors, how long you will manipulate the sensors also will change, okay, in order to have the successful attacks. So spoofing might seem easy, but actually it depends on multiple factors. And here is an example video very quickly I would like to show you. So you see here, Arduino Pilot has 2 different versions, 3.5 and 4.3, okay? And we are applying here on the simulator acoustic noise injection attack. Basically, we are manipulating the sensor values of an IMU sensor. 3.5, the same attack results in crashing on the ground, but in the newest version, nothing happens. Because the way that how developers implement the filter algorithms on the control side is totally different. So if you really want to have a successful attack, then you need to consider all these factors on Arduino Pilot 4.3 in order to make the attack successful, so that developers can easily reproduce such attacks and then they can fix it. So unfortunately, if we try whatever explained in the in a paper, reproducing attacks are extremely difficult because they are only considering the one specific or sensor or very basic control software that doesn't include any filters or multiple EKFs. All right, so I will switch to self-driving cars. If you have any questions so far, I can spend some time to answer them. Or I can take the questions at the end as well.
Quick question.
Sure.
What's better in the 4.3 version? What did they do that fixed the problem?
So 4.3 version, the developers implement more filters on the control software side in order to basically remove the noise from the sensor measurements. And this prevents the attack. So in order to make the attack successful, you need to increase the intensity of the spoofing and also duration of the spoofing. But then it might be detected very easily. Does it answer your question?
Yeah, thank you.
All right, good. All right, so let's move on. So all the prior things that I explained to you was related to robotic vehicles, basically the drones, right? Vulnerability identification for the logic box, and then we little bit touch onto the sensor spoofing, which becomes extremely hot topic. I see in research, I see in security conferences, there are a lot of recent papers in this domain. So when we look at the autonomous vehicles, to me, autonomous vehicles are more complex than drones, okay? The reason is that they have also multiple components, but some of these components, or almost all of them, are data-driven components which are built on deep learning algorithms, okay? And then the pipeline is also, as you see here, it starts from perception, prediction, planning, control, and then the actuation. So I'm also working on the Campbell side, which is like the full control. But also, you know, like from perception to control, there are lots of interesting topics that we can talk about. So the first thing that I would like to tell is you can easily attack the perception, okay, either like in the physical environment or as a digital, because you can modify the environmental very quickly by introducing some noise or by using some patches. So for instance, in this case, if you put a simple trigger to the car, that car can be detected by a vehicle as a person, right? So many people actually in adversarial machine learning uses this as a motivation for their papers, right? But this is extremely easy. And if you misclassify an object, then the consequences also might be very serious, right? If there is a person, for instance, you will assume that the velocity is very low, you can just emergency brake. So while analyzing many papers in this domain, what we have realized is, I mean, there is no solution that effectively can detect. So we were trying to kind of brainstorm some ideas. And we asked this question, like, can we exploit the inherent properties of objects to identify the misclassification attacks? However, in order to do this, we need to answer a bunch of challenges, such as what are those properties? I mean, if we use those properties, like, will we get some low false positives or negative rates, right? So this is the idea. So we say that for each different object, the shape and the location, basically special properties, and the dynamics of bounding boxes over time, which we call temporal property, are different. As you see here, the car and the person, for instance, moves differently, and their bounding boxes are differently. So maybe we can just leverage these simple features in order to detect the misclassification attacks. Okay, so this was our initial observation. In order to test this observation, we kind of do some statistical tests. Okay, so from a field, the field view of a car, we plotted like other cars, and also we plotted pedestrians as well. So on the left, two figures shows at one frame, okay, how the cars and the pedestrians are distributed. And on the right, you see conditional property, conditional distribution, which means that I see a car or pedestrian at the center, and after like 2 or 3 seconds later or time frames later, how their positioning is changing. So the statistical tests kind of confirm that different objects has different movement patterns over time, and their bounding boxes are also different. Okay. Then we start doing some experiments. We simply leveraged the bounding boxes over time, let's say 4 or 5 time frames, and we used a recurrent neural network, okay, by using some existing data sets. They have like a lot of videos recorded in cities or different places. And we built this classifier, basically true and RNN. It's a kind of supervised classifier, okay? So then we use this classifier in order to test our hypothesis. As you see here, if attacker uses a patch size, let's say 20 times 20, the attack success rate is only 0.3 because our detector can easily detect. In the previous example, I mean, if you are changing a car to the person, I mean, we can easily detect because the bounding box over time doesn't look like a car, right? But this is not enough to claim that you are creating an effective defense, because you need to also consider the adaptive adversaries. Like, what if the adversary knows our detection system? So the goal of the adversary is now this. The adversary will try to make the car to the pedestrian, but also the adversary will try to change the bounding box look like a pedestrian as well. You can basically create a joint optimization function, and then you can find the perturbations or the triggers, and you can achieve this. And as you see in these results, okay, if we consider adaptive adversaries, the attack success rate increases. Basically, the adaptive adversary can easily evade our approach. For instance, if an adversary uses 60 times 60 patch, okay, the attack success rate is 12.6. Okay, so our detection rate basically decreases if we consider the adaptive adversaries. So then we ask this question, okay, how we can make our detector more robust, right? Then we said, okay, instead of using spatial temporal features, let's use also contextual consistency. So what is contextual consistency? You can use your speed, or you can use the speed of other vehicles around you, their relative positions. You can even integrate the speed limits as well. Okay, so we have now the spatial temporal features. Now we just merge with the contextual features, and we improve our RNN by using these multiple features in this case. Okay, so this basically helped a lot. The reason is this, because the adversary right now will not only from LiDAR as well. First of all, you need to assume that the attacker has access to the LiDAR as well, or the speed sensor on the canvas as well, right? So this kind of creates the attack difficulty, makes it harder. But also, you know, by using multimodal information coming from different sensors and environment, the attack success rate also drops. So if we assume the attacker has an access to the camera, vehicle speed sensor, VSS, and LiDAR, the attack success rate becomes 24.8. Okay, so we did also some real-world experiments. So at the Purdue campus, we had a talk with the police station here, you know, and then we just put some LCD monitor at the back of a U-Haul truck, and then we just put some noise or some patches there, and we tried. And I would say this, having real-world experiments much harder than doing like digital experiments. As you see, most of the time, we are working on closed environments and after sunset. Otherwise, you need a very big or powerful projector in order to cause the same effect. And there are lots of also uncertainties in the environment as well. But under these controlled scenarios, we have a high detection rate, which is 96. All right, so this technique was, again, purely for misclassification attacks. However, the pipeline of the autonomous vehicles is not only object detection. Object detection is only the first component. To me, the most important part is object tracking. As you see on the right top, You need to track objects over time. This is extremely difficult problem because think about it, right? You see two people at time 0 or time 1, and then in the next time you see another person. Okay, which one is which one? This is a problem of object tracking. So there are a lot of different algorithms. Single object tracking algorithms, multiple object tracking algorithms. And some of the object tracking algorithms uses object detection. This is called tracking by detection. The other ones doesn't use object detection, but they just have a single system which is able to basically track the objects in time. All right. So, I mean, there are some challenges. I see every year in computer vision conferences a paper about tracking, and it's extremely important. So now let's think about it, right? If you are tracking objects, if you are an adversary, what you can do? Each object is associated with a unique number. You can swap those numbers. You can assign new numbers. That's also possible. You can delete maybe some object. Or maybe like if the object is going right, you can move it to the left. So these are from an attacker's perspective. If you can achieve this, overall, you will impact the final decision made by the vehicle or a surveillance system. I would say that object tracking algorithms are widely used in multiple systems as well, not only autonomous vehicles. Okay. So here you see different types of object tracking algorithms. One of them is like sort variants, which is very popular. And the other ones are the Siamese-based. The Siamese-based are more employed in real-world scenarios, especially in the surveillance case. So we define the attack goal. We would like to say that, okay, if you are tracking an object, I would like to make that object move in or move out. Okay. The goal is this. If you move in a vehicle, let's say it's on the side of a road, and then you make it on the middle of a road, then you will stop the traffic. So there are some advantages for the adversary as well. Okay. So to achieve these goals, we created a framework. And every framework that we design, we aim to make it work in the real world. Okay. So we just don't want to use only digital videos. We would like to test it in the real environments as well. So to do so, first what we do is, given a real-world environment, we find the areas that we can perturb. As you see here, the figure in the middle, there are red places that the adversary can basically perturb, or I would say project the noise. Then we make the problem as an optimization problem. Okay, we define a loss based on the based on how the object tracker works, and we solve this optimization problem, and we generate some noise patterns. Whenever attacker puts these noise patterns to the attack zones, like I would say attack zones, okay, the name of the framework is attack zone, then we expect that the attacker can move in or move out the tracker results. All right. So I will show you some example. We did extensive testing. We use some data sets from Carla simulator, or we use like some real world data sets collected, which is called VOT. And then we did like a lot of real world experiments as well. The point here is this: in real world, because you want to generate these patterns, right? You can do offline attack or online attack. Online attack means you target someone, you observe where it goes, and then online you generate these noise patterns and then project them in the environment. But this was a little bit difficult for us. So we did like some offline attacks first, and then we did some online attacks as well. As you see, the online attack results sometimes goes lower. Okay. So let's look at a very simple example over here. So this is Purdue campus right now. Okay. So we are tracking the vehicle in the front. So it's doing a good job. Okay. It tracks well. But at some point, the tracker is move out. It goes to somewhere else. And the reason is the perturbations on on these traffic sites. As you see, it's we just project some perturbations there. I mean, similarly, you can have the same effect with the surveillance system as well. As shown in the yellow square, when someone enters a building, we can project some noise on the wall and then make it like going out of the building. Okay. So if you have never ever worked on tracking, I think tracking is like very interesting and their implementations are very complex. Plus, some of the tracking algorithms, it's very difficult to use gradient descent approach to find the perturbations because there are some non-differential parts of it. All right, so this is the last research that I would like to explain. So we create a defense for misclassification attacks, and then we create an attack for object tracking. So recently, our paper got a shepherding in Usenix. We are working on some defense techniques against object tracking as well. But this topic is like kind of like a new attack vector, okay, for autonomous vehicles. So what we are trying to achieve here is very interesting. Alvaro has some work in this domain. Actually, we are influenced by that work as well. Which is an amazing work. But this approach is like kind of, I would say, a little bit more comprehensive. So the victim car is the yellow car here, and then the victim car just travels on the road. But we have an attacker car. So this attacker car tries to make some adversarial maneuvers next to the victim car, with the goal that the victim vehicle will fail to achieve one of its mission. For instance, if it's a lane following, the victim vehicle, because of these adversarial maneuvers, will fail to follow the lane. Okay, so this is a very quite complex paper, and we did like a lot of experiments, but I will try to summarize you here at a high level. So first of all, we define some missions. Which vehicles, depending on their SAE level, SAE 2 or SAE level 3, which missions they need to achieve. Because our goal is to falsify those missions, right? But while doing these adversarial maneuvers, the other factor is this. We would like to have a low liability. This means that we would like to have the attacker safe, and also the attacker can deny that this mission violation of a victim vehicle is not attacker's fault. So to do so, we have also defined in linear temporal logic a set of rules that the attacker should be constrained while achieving her end goal. Okay. So, I mean, we were trying to use some genetic algorithm or other type of algorithms, but they were very black box to us. So for that reason, we designed our own approach. So given a vehicle, as you see here, we first of all divide a grid, okay? We have a grid. So this grid has a lower bound and upper bound depending on the steering and the throttle of the adversarial vehicle. So after we have that, what we do is, I mean, the point here is that, again, like similar to PGFAS, we need a kind of oracle in order to see whether the victim vehicle is close to the violation or not, right? So here we are using two things, time to collision and distance. So this gives us a hint whether the victim vehicle is violating its mission or not, okay? So then what we do is we kind of randomly sample from this grid, and then we check how close victim to the policy violation. And we constrain the area, and then we again sample from those areas. So here in the yellow part, for instance, we constrain the area in this point, and then we do it again. And this happens like every time, okay? So you give a comment, you check how close the policy violation victim is, and then constrain the space, and then give another maneuver or another command to the adversarial vehicle, and then you continue. You can continue like 4 times, 5 times, 6 times. This depends on your algorithm, okay? So, I mean, experimenting of this framework was like extremely hard. First of all, we picked like some places that we can run our algorithms. And then we initialize the setting. We position the adversarial vehicle in different places. And then we start running the algorithm, okay? We have found like over 340 different successful attacks, okay? Out of 7,000 trials. So I would like to show you one example, which will make things a little bit concrete. So here, adversarial vehicle, as you see, did some adversarial maneuvers, but the vehicle didn't stop, but crashed to the red car, right? So again, the goal of our framework is to find such adversarial maneuvers, but also keep adversary safe, plus also ensure some deniability so that you cannot accuse the adversary. For instance, adversary, I would say, when there's a stop sign, it stops. When there's a speed limit, obeys the speed limits. When there is a crosswalk, it stops on the crosswalks. Okay. So you might be wondering right now, right? Like why that maneuver caused an issue? Why make the open pilot fail to stop? The reason is this. This is all manual analysis. Okay. So if you look, this is how, for instance, open pilot sees or detects the cars in the front, two of them together. But at some point, because of due to the maneuvers, these bounding boxes are merged together. And then the software might think that there is a single vehicle or something single in front of me, but it's moving. Because even though the red vehicle is stopped, the other vehicle is moving, right? So that's the thing. And then, of course, it doesn't stop. So this is kind of a new attack, right? Like merging the bounding boxes or merging multiple objects bounding boxes in a single object and introducing some velocity on it. And then the vehicle will not stop. And there are also like some other reasons why these trajectories can happen, why these adversarial maneuvers can be successful, such as planning model error or the perception model error. All right, so this is a summary. I think in autonomous vehicles, composition is extremely important, and you can exploit the composition, basically interacting components, and find very interesting research problems. The second is this. It's very difficult to formally prove that your algorithm is sound and complete. For instance, I just show you an adversarial maneuver, right? You can ask me this question, Berkay, can you prove me this is due to the 100% to the adversarial maneuver? And we tried, like, we repeat the experiments in different weathers with different cars, but I cannot still prove you this is because of the adversarial maneuvers. High likely to be with adversarial maneuver. Why? Maybe another object or maybe a simulation error might be causing that. And I cannot perturb everything, right? I cannot intervene everything to give you a proof. Okay. So another thing, which is also challenging. If you only do simulations, most of the time reviewers will not like it. So you need some real world experiments. Okay. So the bar is getting higher and higher every day. The fourth thing, adaptive attacks. If I read a paper without an adaptive attack analysis, really, I'm not sure whether this approach is good or not. So in all work, we try to integrate adaptive attacks, and we try to show that our methods with some budget, perturbation budget, or with a cost will work or not work. So we show the success rate in these cases as well. Also, from a student's perspective, I mean, my students need to know about deep learning. They need to know about formal methods. They need to know about program analysis. So it takes 2 years, 2.5 years to train the students to know all these type of things. I'm not mentioning how to use these simulators or how to improve these simulators. For that reason, I like to collaborate with different people, such as here, like Ricardo, Alvaro, or Daniel. And the other thing is, in this domain, we are missing a lot of benchmarks. Computer vision, people has like some benchmarks, but in security community, like for object tracking or object detection, people are using all different type of data sets. A unified benchmark environment would be great for our environment, for our research. All right. So today, even though I told you about compositional secure autonomy, I like to explore different things. These are like 3 themes that I'm doing. And if you are curious about any of them, we can talk later. You can send me an email. The other themes are privacy sensitive information flow control. Okay. And we have a lot of work in this domain. And due to the COVID being single, I'm exposed to social media a lot. And every time I use the social media, I always like see some weaknesses or something going unusual. For that reason, you know, like recently we made all these, I would say, you know, the ways that how the social media can be exploited by people, turn them into papers. So which I call this like security, privacy, and online trust in online platforms. And lastly, I would like to thank my sponsors and my students. They are working really hard. We created a very nice research culture here at Purdue. Some people work on autonomous vehicles, some of them are drones, some of them are AR, VR devices, but they have all amazing skills. They collaborate with each other, and without them, these papers cannot happen, basically. Thanks, everyone. If you have any questions, I would be more than happy to answer them.
So, do we have any questions in here or in Zoom? No questions. So, yeah, I have a quick question, I guess, based on your. I think that the second result that you presented on the physical attacks or the reproducibility of sensor attacks. I've seen a lot of discussion of whether or not these attacks are practical. So I wanted to see what is your impression. So I know that in some limited example or constrained conditions, you can always launch these analog attacks. But in your experience, how do you see this field moving forward? Is it easy to reproduce in the real world, or what are the major challenges that you see? I know, yeah. I mean, I know your presentation is part of this work, but I wanted to see what, like, moving forward, how do you see this?
Yeah. The first thing. Okay. So very good question. So this is basically our recent paper, which is accepted to IEEE Security and Privacy. It's online. You can read the details there. I think sensor spoofing becomes important because of the recent events in Ukraine, Russia, and Israel in the Middle East. There are a lot of use cases of drones, and one way to have these drones kind of address these drones, I would say, is spoofing, because otherwise you need to spend a lot of money to hit those drones, right? Like maybe the drone is like 100K, but you are spending $1 million for it, right? So it's interesting in that sense, and I know that agencies also puts a lot of effort to have a workforce in this area too. DARPA has a FIRE program recently. If you check that out, it also focuses on sensor attacks. So I think it's important, but the goal is this. Developers do not believe that these attacks are very easy to conduct. And then when you report them, they try it, and then they cannot reproduce them. Okay? I mean, in theory, if you manipulate something, you can have, right, some consequence. So our goal here was try to at least identify those reachable states. Like really, if you would like to make this attack successful, you need to consider all these different components, and then you can reach to the end goal. But I think I would say that existing papers, I'm not sure whether they need to pay attention or not. They don't pay attention, but in their environments, the attacks are successful. But if you port that attack to the, like any other drone, even I showed you, right, different software versions, it doesn't work. Then this becomes like, how I can make it work? Is it feasible with the equipment that I have? Or should I have like a kind of a different thing in order to increase the intensity of the acoustic noise injection attacks? So overall, I'm thinking it's a very important research area, and I think there will be more papers in this domain.
Okay.
I have one last one. How much do you rely on models of the system?
The models of the system.
Yeah. How much do you rely on having accurate models of the system? I couldn't get that from, I think it's more like model.
Yeah.
Model not based, or how you call it, model free, right?
So we are using right now in many works that I mentioned you, like in the reachability analysis, we don't have any model. So we are using directly the software, and then we are hooking how that manipulated sensors values propagates through each component of the either operating system or the control software, right? So we don't have the model in this case. We are using the system as it is in a simulation environment. So think like this. We track the sensor values and how it propagates to the actuation commands. So this gives us the holistic view of how to make the attack successful or why the attack is not reproducible easily. So that's the goal. So does this answer your question? So I'm talking regarding the sensor spoofing and reachability analysis.
Right. Yeah, thank you.
But I would say here, we use a lot of model-based approach too, especially with my student Özgür. We kind of like model smart homes, for instance, as a time automata in order to understand the physical interaction between different devices. But today I didn't include them in my slides.
Thank you.
Okay, well, thanks again, and let's give a round of applause.
All right, thank you so much again for hosting me. I think I can stop sharing now.
So I think we asked, yeah. We have a couple of meetings if you're available. I don't know. So I think, yeah, my students are here, Luis and Diego. So yeah. Yeah, right. Sure, yeah, I can contribute there.
So usually break.
Right. Okay. Yeah. I was thinking, yeah, if you want to take a break or take a restroom break or something, and we'll be here. Maybe we can reconvene in